Okay, I also want to start out by thanking the organizers for inviting me here. And I want to thank Hugo for giving a very good introduction to what I'm going to be talking about, which is trying to access correlated electron motion on attosecond timescales. Just a short overview after the introduction. I'm going to be talking about two main topics, mostly attosecond streaking, where the goal is to extract time delays in atomic photoionization, where we are interested in figuring out what the real origin of the measured time shifts are. And then I'm going to be talking about the method for doing an attosecond pump, attosecond probe experiment using two-photon interferometry. So just as a general introduction, why are we interested in attosecond physics? What happens on attosecond timescales? The general or the most often given example is the orbit time of a classical electron in the ground state orbit of the Bohr model is about 150 attoseconds. So we already know that timescales of electron motion in atoms or in molecules or in solids are on the attosecond timescale. And a somewhat more complicated example is actually from the group of Lorenz Sederbaum that I'm going to show you a short movie, the dynamics of electron charge redistribution inside this very complicated molecule that I'm not going to try to pronounce. And if I start this movie now, you see that within, let's say, sub-femtosecond timescales, you really see a redistribution of the electron charge inside the molecule. And these are the kinds of dynamics that you might want to access or even control directly. And you have, in all of these cases, many electrons involved, and the relevant information of dynamics is encoded in the phases. So what tools do we have to access these dynamics or to control them? Basically, there's two main things. One is few cycle infrared laser pulses, which are at least a few femtoseconds long. And the other is attosecond extreme ultraviolet pulses. And really the point you have, or the thing you need to get down to these very sub-femtosecond timescales in terms of control is that you can control not only the amplitude of these femtosecond pulses, but that you can really control the electric field, so that you have a reproducible electric field. In every shot you have exactly the same electric field in your femtosecond pulse. So yes, that you have carrier envelope phase control, basically, and that allows you to also produce these attosecond pulses. Okay, what we want to look at with these tools then is actually multi-electron effects or correlation effects, and what we mean by that is basically that the wave function is not a single Slater determinant, that it's not just a single product of single particle orbitals. And the atom that we use mostly for looking at these kinds of effects is helium, for a few reasons. First of all, it's the simplest many electron atom, which means that we can still treat it relatively precisely with calculations, and it already has rich correlation effects. So we can do full numerical simulations and look at all of these correlation effects in quite a lot of detail. The method we use for that, I don't want to go into too much detail. It's a much more, let's say, straightforward method than the very complicated R matrix. We have the Hamiltonian for the time-dependent Schrödinger equation with the Hamiltonian for helium. We use a non-relativistic Hamiltonian. We assume that the nucleus is infinitely heavy. We use the dipole approximation. And then what we have is basically 6 spatial dimensions, which reduce to 5 if we have cylindrical symmetry in linearly polarized fields. And we have time, since we look at the time-dependent Schrödinger equation, which means that overall we have a high-dimensional object, which makes it computationally quite demanding to solve this. And what you want to do is choose discretization and propagation schemes for these equations that ensure that you can do this efficiently and also, and importantly, that you can parallelize well. And the schemes that we have chosen, I don't want to go into too much detail, but basically what we find is that we can parallelize well enough that we get linear speed up, and we've tested that with up to 1800 processors. So that enables us really to do a lot of simulations and to look at the results in detail and still ensure that we have converged results. Okay, so with that I want to come to the first physical application, which is attosecond streaking. What's streaking, or why streaking? The classical streak camera, so to say, is a method of mapping time information about the laser pulse to position information on the screen, where the idea is that you shoot some time-dependent laser pulse onto a photocathode. The emitted photoelectrons pass between these two plates. You have a voltage ramp between the plates, and depending on when the electrons pass, they get deflected by a different amount and then end up on the screen with a position shift that depends on the time when they reach the plate. So in this sense, you have a mapping of time to position. And amazingly, in my opinion, they can go down to around 100 femtoseconds time resolution with this kind of classical setup. But of course, that's not fast enough to look at this attosecond dynamics that we want. So what we are looking at is this method of attosecond streaking, which is somehow extending the same idea to this combination of an attosecond extreme ultraviolet pulse that will knock down out the electron. So that's the same photoelectric effect. And then we accelerate the electron now not by the classical electric field between these two plates, but by the electric field of the synchronized infrared pulse. There again, we need this perfect control over really the electric field of the infrared pulse. And when you now scan the delay between the attosecond pulse and the infrared field, what you get is that depending on when the electron is emitted from the atom, it gets accelerated or decelerated by the infrared field by different amounts. And basically what you have, the electron comes into free space out of the atom, and then the momentum shift it acquires is just the integral over the electric field from the moment of ionization, and that's just the vector potential of your light wave at the moment of ionization. So in that sense, you have a direct measurement actually of the light wave, or of the vector potential of the light wave, which was the first application of this kind of setup. But what you also get is a mapping of the time of ionization to momentum, and you can use that to actually get information about when your electron was kicked out of the atom in some sense. So these kinds of measurements were also performed using these techniques, and the first one was about 10 years ago using proof of principle, showing that you can actually measure the lifetime of an Auger hole in krypton directly in the time domain, which is around 8 femtoseconds. Then 5 years ago, it was shown that in emission of electrons from a tungsten surface, the core electrons from the 4f states are actually delayed with respect to electrons from the conduction band by around 110 attoseconds. And the application I want to focus on is photoemission from atoms, from neon specifically, the same that Hugo was talking about, where it was found that photoemission from the neon 2p shell seems to occur somehow 21 attoseconds later than photoemission from the 2s shell. And just quickly, how does this experiment work? You have the neon atom with its 10 electrons. The XUV pulse kicks out an electron either from the 2s or from the 2p shell. And what you get is, again, these streaking curves where you here have the delay between the attosecond pulse and the infrared pulse. And the higher energies are the electrons that were emitted from the 2p shell. The lower energies, the more deeply bound ones, are the electrons from the 2s shell. You cannot see it on this graph, but if you look in detail, these two curves are basically shifted horizontally to each other. And this shift is the time delay between the two emissions in some sense. And surprisingly, what you find is that actually the slower electron that's more deeply bound seems to come first, which intuitively seems a bit surprising because it has to come out from deeper out of the atom. But the real question is, of course, what are we actually measuring? I mean, what I've been talking about are very simple pictures, but to get some idea of what could we be measuring, we have to think about in scattering, which photoionization somehow is, what actually is a time delay, what could we access. So in a very simple 1D picture, scattering is described in quantum mechanics basically by a wave coming in and a wave going out, and all the information about the scattering event is encoded in the scattering phase. And already more than 50 years ago, it was shown by Eisenbart, Wigner, and Smith that the time delay in scattering, if you take a wave packet here around the energy, around this energy, you get a time delay which is the energy derivative of the phase. So again, the dynamical information is encoded in the phase of the matrix elements. That's this Eisenbart-Wigner-Smith time delay that you could hope to access in the streaking, and that would be the time delay of photoionization, which just is scattering with the photon coming in and an electron going out. So if we now try to do this for hydrogen, We say we take the simplest atom that we can. We know we can solve that completely. We see it doesn't work, at least not as you would expect it. The Eisenbart-Wigner-Smith delay is this dashed line. This is now as a scan of final electron energies, or equivalently photon energies. And the streaking delays that we extract are this line. So the sign is shifted, doesn't seem to work. But that's not too surprising, in fact, because the simple picture assumes that the electron is in free space when it gets accelerated by the electric field. But of course, an ion has a long-range Coulomb potential. So the electron is actually moving in the combination of an electric field from the laser plus a Coulomb potential. So the momentum shift it acquires is not just the integral of the electric field strength, but it is modified by this Coulomb potential. And it turns out that this so-called Coulomb laser coupling shift can be reproduced already by classical dynamics. You can also reproduce it by quantum dynamics as the phase of basically the continuum matrix element. And what we can do is, since we know the Coulomb potential is the same in all targets, we want to know the interesting information, which is the short range interaction between the two electrons. And then you always have the long-range Coulomb tail. So we can just say we take this Coulomb laser coupling shift, which should be the same in all targets, and subtract it out, or add it to the model that we have for the streaking shift. And what turns out is you can perfectly reproduce the numerical results, which is this red line. So if we test this now for, let's say, a somewhat more interesting model, which is in this case a model potential for neon, so still on the single active electron description, but using a model potential. We have here again the calculated Eisenbart-Wigner-Smith time delays. We have the numerical results, and now if we add the Coulomb laser coupling term to the Eisenbart-Wigner-Smith time delays, we get perfect agreement between the two. So it seems that we can actually, in fact, access this Eisenbart-Wigner-Smith time delays of the atoms as long as we take into account we have this Coulomb laser coupling term. But I want to point out, at least for this mean field model of neon, which is not the only one that's out there, but most of them are similar, the delay we find at the photon energies which are used in the experiment is this difference, which corresponds to around 7 attoseconds, whereas in the experiment there were around 21 attoseconds of time delay measured. So the next question is, this is a single active electron model, are there any correlation effects? Are there any effects of the electron interaction being somehow modified in the laser field that then give you an additional time shift? And for that, since we cannot do neon, and Hugo was just talking about how difficult it is to do these calculations for neon, we use helium as a model system. And there we don't have different shells, obviously, but we have so-called shaker ionization. So in helium, when we kick out an electron, the normal process is that you kick out the electron and the ion remains in the ground state. But because of electron correlation or electron interaction, you can also excite the remaining ion and leave it in an excited state, for example, 2s or 2p. And what you get then in the energy spectrum are these so-called shaker peaks or correlation satellites, which are at offset in energy. And if we now again do this streaking, so these are now relatively heavy calculations, let's say, but still not too bad. We get this streaking picture, and we can again extract the time shifts between these two different curves and compare them to our model. And if we do this, we find for the 1s electron, so for the ion left in the 1s state, this works perfectly well. So the line is again the model of Coulomb laser plus Eisenbart-Wigner-Smith time delays, and the squares here, the numerical results. But for the excited states, for 2p and 2s, and also for the average of the n equal 2, we find that this does not agree at all with the model that we have. So there's some additional shift in there, which might be because of electron correlation. And if we look into this in more detail and think about it, we realize, of course, the helium plus ion 2p, 2s are degenerate, and this degeneracy is broken inside an electric field. And what we are doing is exactly ionization inside an electric field, because we have the infrared pulse at the same time. And the eigenstates of the ion in the infrared pulse, if we say, since this is a relatively slow pulse, this is a quasi-static field, the eigenstates are 2 plus and 2 minus, instead of 2s and 2p. What we see is if we project on these as final ionic states, we see a much larger effect. And that's the first hint that we are on the right track. And if we go into more detail, we find out we can actually model this additional time shift that we see very well by just taking the approximation of saying that the infrared field, since it's much slower than the dynamics that happens, is basically a quasi-static field. The Stark states have a permanent dipole moment, which means that the ionic states have an energy shift in the quasi-static infrared field that depends on the moment of ionization. And since the electrons are correlated and interacting, the energy that the free electron gets depends on the energy of the channel in which it's emitted. So if I emit an electron into, let's say, the 2+ ionic state, the free electron will get either this additional energy or lose the energy of the dipole in the electric field. So you get an additional energy or momentum shift on the free electron depending on the ionic state because of this entanglement. And this shift looks like a time delay exactly because streaking is a mapping of energy shift or momentum shift to time delay. And it turns out you can, if you include this, you really get a perfect agreement between the shift you extract from the numerical simulations and the prediction from the model, where you just now include this electron-electron Coulomb laser coupling somehow, where the electron-electron interaction is modified by the presence of the infrared field. And now, by taking into account the 2s and 2p channels are just coherent superpositions of the 2+ and 2- channels, we can reproduce also the numerical results for 2p and 2s, and also, of course, the average, the incoherent sum. And interestingly, this effect survives even for the incoherent sum of n = 2. So you have to take this term into account also for this incoherent sum, where you would assume a priori maybe that the directionality does not matter, that you would average out of these directionality effects in the electric field. But it turns out that you still get a sizable shift because of this. Okay, so and with this I'm already basically finished with the streaking part. What I showed you is that we managed to basically quantify the multi-electron streaking time shifts on the sub-attosecond level. So really, the model agrees with the numerical results with an error below 1 attosecond. And what you just have to include is this Coulomb laser coupling. You have the Eisenbart-Wigner-Smith time delay, which is somehow the most interesting part in terms of accessing new information that you cannot get with any other kind of spectroscopy. And you also have this laser-modified electron-electron coupling, at least if you have easily polarizable degenerate final states. One part that I don't want to talk about in too much detail, but that I want to mention is that for a 2-electron model system with a model potential that somehow reproduces the energy structure of neon, we don't want to call it really a model for neon because it's really quite far from that, but the energies are roughly there. We find that we don't see any additional correlation effects apart from this laser-modified electron-electron coupling, which actually does not play a role here because the final states are not polarizable. So the next step here would be to try to apply this model to neon, and we've been working on this in collaboration with Klaus Barchert and Oleg Zazarini, who have R-matrix structure calculations where they can calculate this phase of the photoionization very well, and so we can get the Eisenbart-Wigner time shift for this part. The Coulomb laser coupling is independent of the system we look at, and the final states are not easily polarizable, so it should be possible. And the streaking shift should be just the sum of these first two terms, and the results that we get are again around 10 attoseconds for the experimental photon energy, and this is actually similar to the results that Hugo and the other people in Belfast obtained with the time-dependent R-matrix. So I think by now we are sufficiently confident in our results that we think that the experiment maybe should be repeated to try to get better statistics and maybe do a scan over over photon energies and so on to really find out what's going on there. Okay, and if I have some time, yes, I want to go to my second part, which is about doing attosecond pump, attosecond probe setups. So why do we want to do this? The standard nowadays in attosecond physics is, as for example in streaking, to use a pump probe experiment using a few cycle infrared pulse with an attosecond XUV. The disadvantage of this is to really get attosecond time resolution, you need to look at sub-cycle effects in the infrared pulse. These are often strongly nonlinear effects, which means that the dynamics get modified by the infrared field and it makes it very hard to interpret, or can make it hard to interpret. And for that reason, using 2 attosecond pulses has been called the holy grail of attosecond physics by some people. The problem with that is that nowadays the pulse intensities are too low to really get 2 photons absorbed from attosecond pulses, just because high harmonic generation is not a very efficient process, and free electron lasers don't produce attosecond pulses yet. And there are not too many useful schemes out there yet for doing attosecond pump, attosecond probe. So not too many people have looked at what could you actually do. So the first part, the pulse intensities being too low, that's what the experimentalists are working at, and there's quite a lot of progress there. In fact, just last year there was already a first paper doing attosecond pump, not attosecond, it was around 1 femtosecond, but still pump probe with in argon. And these are other papers showing the increases in high harmonic efficiency. And of course, there's also the work of getting free electron lasers down to below femtosecond pulses. So either of these could lead to enough pulse intensity in attosecond pulses to enable this kind of pump probe with 2 attosecond pulses. What we want to look at is a possible scheme for looking at interesting correlated dynamics here. So what we want to look at are the doubly excited states of helium, which exist because the electron-electron interaction is in the Hamiltonian. And what that does is that you have in the spectrum of helium these doubly excited states, which are almost all autoionizing resonances, which are very strongly correlated states. So for these states, really, the single orbital picture breaks down, and you have to use collective quantum numbers to describe them. So from this point of view, they are very interesting in terms of correlation. And the scheme that we want to use, the simple idea for probing this is really straightforward. You pump them, you use an attosecond pulse with a photon energy or wavelengths that's tuned to a transition to more or less the first doubly excited states in helium. And if this is broad enough, you create a wave packet of these doubly excited states. Then you wait for some time, you let them evolve, and then you want to probe the correlated dynamics by using another pulse, and in our case we take an identical pulse to kick out both electrons and look at double ionization. The problem with this scheme is that you have in both steps, both in the pump as well as in the probe, one photon transition that has to talk to both electrons, because you have to excite both electrons into the doubly excited states with one photon, then you have to ionize both electrons with one photon again in the probing part. But if you look at this scheme in more detail, you actually realize it's not as simple as what I just wrote down, because we're using 2 identical pulses, which means that you actually have 3 paths for 2 photon absorption that all lead to the same final states. And these are either you can absorb 2 photons in the pump pulse already and go directly to the double ionization, or you can actually stay in the ground state and absorb 2 photons just in the probe pulse, or you can go through the path that you're actually interested in, which is 1 photon from the pump and 1 photon from the probe. And the dynamics you have then in this superposition here contains actually quite a number of time scales. You have here the superposition of doubly excited states, which evolves on a scale of a few femtoseconds, which is basically given by the bandwidth of your pulse, so the bandwidth of the wave packet that you excite. And you have a very fast beating, which is basically given by the energy difference between these doubly excited states and the ground state, which both interfere then here to go to the final state. And for reasons that I don't want to go into too much detail on, the path alpha basically just gives an incoherent background for most of the observables that we look at. And so if this is the electron energy distribution you get in the end, and because of time constraints, I don't want to talk about this in detail. But basically, the idea is, this is the 2 electron energy distribution, energy of the first electron, energy of the second electron. And what we propose to use is just this cut of the electron energies and just measure the single electron energy spectrum. And this means it's a much easier experiment than trying to measure both electrons, which you would usually want to do for correlated electron dynamics. So we only want to look at the single electron and some energy selection. And now the important idea is really to use this two-photon ionization, double ionization out of the ground state, which is this pathway gamma, as a reference wave, because this is independent of the time delay. This is always the same process, as a reference for the pump probe signal through the path beta, where you have the interesting double excited state dynamics. And what this gives you, the signal that you get, the ionization probability as a function of time delay, you get this fast oscillation, which is the interference between the ground state and the double excited state wave packet, which is not really the interesting part. But then this fast oscillation is modulated with an envelope, which is basically given by this interference between the ground state, or the path gamma, and the double excited state wave packet, the path beta. And this slow modulation of the envelope on a femtosecond time scale is what actually encodes the double excited state dynamics. And the question is, of course, what kind of dynamics can we see in this setup or in this scheme? And what we show here is, first, in the blue line, the yield just from the double excited states, which is what you won't actually see in the experiment because it's too small. And then the red line is this interference term, which modulates the envelope of the fast oscillation. And as you see, this is around 100 times larger than the signal from just the double excited states, but otherwise reproduces it almost perfectly. And the green line tells you what observable you are actually sensitive to here, which is basically the distance between the two electrons, so the inverse distance modified by the dipole operator. So you're basically sensitive to when the two electrons are close together in this correlated two-electron wave packet. When they're close together, of course, it's easier to ionize both of them at the same time. So you get large double ionization when the two electrons are close together. And that's, for example, on this plot, you see this. This is the electron distance for this point. You see that they tend to be much closer. And here, when they're further away from each other, you get basically no double ionization. So this is already the summary for this part of the talk. So I've shown that this pump probe scheme gives access to the correlated two-electron dynamics in the double excited states. We only need to measure a single electron spectrum with an energy filter. And the main idea is to use the single pulse two-photon double ionization as a reference wave for the interferometry. That's what gives you this increase of 2 orders of magnitude in the signal, which might be enough to do it in experiment, at least in a few years. And with that, I want to finish and thank all of my collaborators, and especially Stefan Nagele and Renate Pazurek, who for the streaking part did all of the real work in terms of numerical simulations and so on. And thank you for your attention.